5.5 Indefinite Integrals and the Substitution Method. The outline of this video is as follows. We will discuss the method of substitution, a powerful technique for finding antiderivatives. We will begin by reviewing indefinite integrals and understanding how substitution acts as the reverse of the chain rule. Next, we will cover the formal substitution rule and the specific steps to apply it effectively. From there, we will investigate advanced examples that require adjusting constants, handling trigonometric functions, and manipulating algebraic expressions. Finally, we will summarize the key strategies for identifying the correct substitution to solve complex integrals. Let us establish the precise definition of an indefinite integral. The indefinite integral of a function f with respect to x represents the entire set of its antiderivatives, written as the integral of f of x dx. Because the derivative of a constant is zero, any two antiderivatives of the same function can differ by a constant value, so we always add an arbitrary constant c to our result. It is important to distinguish this from a definite integral, which computes a specific number such as area. In contrast, an indefinite integral returns a function family. The essential takeaway is that you must never forget the plus c when solving these problems. Substitution is essentially the chain rule applied in reverse to solve integration problems. Recall that differentiating a composite function like u to the power of n plus 1 produces a result involving u to the power of n multiplied by the derivative of u. Integration by substitution exploits this pattern by identifying a part of the integrand as the derivative of an inner function. By rewriting the integral in terms of u and its differential du, we simplify the expression into a basic power rule form. This allows us to integrate u to the power n directly. This method converts complex composite functions into simple, solvable integrals. We will now demonstrate the basic substitution method with a polynomial example. The problem asks us to integrate the quantity x cubed plus x to the fifth power multiplied by 3x squared plus 1. We set u equal to the inner polynomial x cubed plus x, which means du is exactly 3x squared plus 1 dx. Since this derivative term is already present in the integrand, we can substitute directly to get the integral of u to the fifth du. This integrates simply to u to the sixth over 6. Finally, we replace u with the original expression to obtain the solution. Sometimes the derivative of your chosen u matches the integrand except for a constant factor. Here, we choose u equal to 2x plus 1, which gives a differential du of 2 dx. However, the integral only contains dx, missing the factor of 2. We solve this by multiplying the integral by 1/2 and the integrand by 2, effectively multiplying by 1. This allows us to substitute du for 2 dx's while keeping the equation balanced. We then integrate u to the 1/2 power to get u to the 3/2 over 3/2. The final step is to substitute back to get the answer in terms of x. Theorem 6 formally states the substitution rule, which justifies changing variables in an integral. It says that if you have a composite function f of g of x multiplied by g prime of x, you can equate this to the integral of f of u with respect to u. This works because the term g prime of x dx is absorbed into the differential du. The proof relies on the definition of the chain rule, showing that differentiating the result with respect to x returns the original integrand. This theorem provides the rigorous foundation for replacing complex expressions with a single variable u. To apply the substitution method reliably, follow this three-step process. First, choose a substitution variable u equal to an inner function g of x and calculate its differential du. The goal is to transform the integral so that it appears entirely in terms of u. Second, integrate this simplified function with respect to u using standard rules. Third, replace u with the original expression g of x to state the final answer. While u is the traditional letter, the logic holds for any variable. The main challenge is simply choosing the correct expression for substitution. Trigonometric integrals often require identifying the argument of the function as your substitution variable. In this example, we integrate the secant squared of 5x plus 1. We let u equal 5x plus 1, which makes du equal to 5 dx. Since the 5 is already part of the integrand, we replace 5 dx directly with du. This leaves us with the integral of secant squared u, which we know is tangent u. After integrating, we substitute the original argument back into the tangent function. The result is simply the tangent of 5x plus 1 plus c. In this example, we handle a missing constant by solving explicitly for the differential term. We let u equal 7 theta plus 3, so du is 7 d theta. Since the integral contains only d theta, we divide our differential equation by 7 to see that d theta equals 1/7 du. We substitute this into the integral, pulling the 1/7 out to the front. The integral of cosine u becomes sin u. Finally, we back substitute to find the answer is 1/7 sine of 7 theta plus 3 plus c. A useful strategy is to look for a power of x in the integrand that is 1 less than the power inside a function argument. Here, we see x squared multiplying e to the power of x cubed. Since x squared is related to the derivative of x cubed, we set u equal to x cubed. This gives du as 3x squared dx, allowing us to replace x squared dx with 1/3 du. The integral simplifies to 1/3 times the integral of e to the u. This integrates easily to 1/3 e to the u. The final result is 1/3 e to the power of x cubed plus c. Sometimes a substitution leaves an extra factor of x that is not accounted for by the differential. Here, setting u equal to 2x plus 1 works for the square root, but leaves an isolated x term. We resolve this by solving our substitution equation for x, finding that x equals u minus 1 divided by 2. We substitute this expression for the x term and replace the root with u to the 1/2. This converts the integrand into a simple polynomial in u that we can distribute and integrate. After finding the antiderivative, we substitute back to express the solution in terms of x. Certain integrals require trigonometric identities to transform the function into an integrable form before substitution. For sine squared x, we use the half-angle identity to rewrite it as 1 minus cosine 2x over 2, which can be integrated term by term. For tangent x, we express it as sine x over cosine x. This reveals a natural substitution where u equals cosine x, making the numerator the negative of du. These examples illustrate that you should check if an identity can simplify the integrand before attempting a complex substitution. Algebraic manipulation can often reveal a hidden substitution. In the first case, we multiply the fraction by e to the x over e to the x. This transforms the denominator into a form where u equals e to the x is a perfect substitution, leading to an inverse tangent result. In the second case, integrating secant x requires multiplying by a special fraction equal to 1, secant x plus tangent x over itself. This makes the numerator the exact derivative of the denominator. Both techniques rely on multiplying by a form of 1 to fit a standard integration rule. This slide summarizes the integral formulas for the 4 basic trigonometric functions. The integral of tangent x is the natural log of the absolute value of secant x. The integral of cotangent x is the natural log of the absolute value of sine x. For secant x, the integral is the natural log of the absolute value of secant x plus tangent x. Finally, The integral of cosecant x is the negative natural log of the absolute value of cosecant x plus cotangent x. Memorizing these standard forms will speed up your work on more complex problems. We can often solve an integral using different substitutions that yield the same result. In this example involving a cube root, method 1 sets u equal to the inner polynomial z squared plus 1, leading to a fractional power integral. Method 2 sets u equal to the entire radical term, which requires cubing u to find the differential. Both methods successfully simplify the integrand and produce the same final expression after back substitution. This shows that if a standard substitution feels too difficult, trying a different choice for you, such as including the radical, might work better. To summarize, the substitution rule is the primary method for reversing the chain rule in integration. The process involves identifying an inner function u, calculating its differential du, and substituting to create a simpler integral. We have seen that you must be flexible, ready to adjust constant factors, solve for x in terms of u, or use identities to facilitate the substitution. Always remember that the indefinite integral results in a function plus an arbitrary constant c. Success with this method comes from practice in recognizing the derivative of a function within the integrand. Please consider the following review questions to deepen your understanding. First, when integrating x times the quantity 3, x plus 2 to the fourth, why is it necessary to solve the substitution equation for x? Consider how the factor x outside the parentheses affects the integral. Second, how does the integral of tangent x relate to the logarithmic differentiation of cosine x? These questions highlight the connections between algebraic manipulation, derivatives, and the resulting integration formulas.